Sine parent function, you guys already saw it, so we kind of should have this like wavy picture in our head as far as what we expect for the sine graph. But we want an actual list of points that we're going to use as a starting function for the sine graph, okay? So we made a much longer chart previously for the sine function, but when we made our chart, it cycled through multiple times. We only want to get one cycle of the graph because then we can expand that later and follow the patterns. So do you guys remember how long it took for the sine function to go through one cycle of points? You guys looked at it when we graphed it on paper. You saw it again in the investigation. For the parent function, how long does it take for you to cycle through all the different values of sine and then you're back where you started and you're doing it again? Say it louder, Sean. Good, 360 degrees, but since we use radians for labeling our graph, we're going to kind of convert that to 2 pi. So we basically want to start our parent function at 0 and end it at 2 pi to get one cycle. And if you guys remember, it was enough when we were graphing it that we didn't need all the crazy points like rad 2 over 2 and rad 3 over 2. We just needed to cycle through like the zeros, the ones, and the negative ones. And so those things happened on the unit circle. The sign was either equal to 0, 1, or negative 1. At these main spots. So our parent function kind of just jumps by 90-degree increments, but written in radians. So from 0, we'd want to go to pi over 2 next, and then pi, and then 3 pi over 2, and then 2 pi. Okay. And you guys will have, it would be very unfair of me to not give you your unit circle because the expectation is in here is that you don't have to memorize. You'd have your unit circle. So even on the graphing test, okay, and the graphing test will contain some unit circle stuff as well, you'll have your unit circle. Okay, so if you know that these are the x values you want, you can find the y values on the unit circle for those by going to those positions and finding the sign. Okay, 0 is here. Okay, so the sign at this point is 0. Pi over 2 is here. The sign at that point is 1. Pi is at 180. The sign there is 0. 3 pi over 2 is down here, and the sign would be negative 1. And 2 pi is back where we started at 0, and we'd have 0. This is the parent function table we want to use for the sine graph. Okay? So your job is going to be to remember that these are the values that you're going to want to plug in for the sine function. And again, probably the easiest way to remember that is the visual of you just want these simplest points to plug in the sign, and you want to do it one time around the circle, so from 0 to 2 pi. Okay? All right, and so then we're going to go ahead and put this on the graph. If you look at our y values, 0 is kind of the middle of the function, and then it reaches up to 1 and down to negative 1. So on my y-axis, I'm just going to number these 1 and negative 1. And then one of the harder things for us will be scaling the x-axis, okay? Here we have 0, and we know the next thing we want is pi over 2, okay? Because I know what our tangent graph looks like and I want your parent functions to look pretty similar, I'm going to say that every 2 marks, it's like a pi over 2. So this is my 0, then pi over 2. The next one would be pi, then 3 pi over 2, and then 2 pi. Okay? So if I wanted to label these ones in between, I don't need to because look at my points. I don't need anything in between. This is enough. But if I wanted to label these, what kind of marks would they be? What is each mark on this graph measuring? If this much is pi over 2, how much is just one individual mark? Half of it. What's half of pi over 2? What's that? What's half of pi over 2? Take the pi out of it. What's half of a half? A fourth, right? So half of pi over 2 is pi over 4. So the reason I'm pointing that out is not that you need it right here, right now, but this is going to probably be the hardest part of creating our new graphs, is scaling it in a way that makes it really easy for us to plot points, okay? So then I'm just going to plot each of these points. So 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi. And I'm going to see that curve that I expect to see, okay? Just one portion of it. When you guys make your final graphs, I want more than one portion, but you don't want to have to do giant charts. You want to get one chart to give you the one pattern, and then you can just continue the pattern if you had to after that by plotting points without doing all the arithmetic for the chart. Okay? All right, so when you guys graph these, we're going to ask you kind of this information each time. So period, how long did it take the sine graph to complete one cycle for the parent function? 2 pi, right? That's why we stopped at 2 pi, because we're going to start over again. And then remember that your frequency is just the reciprocal of that. Okay? And that's going to come in handy when we're working on our project. Amplitude. Okay? What is the amplitude of this graph? 1. Okay, so remember, amplitude is you kind of have this midline of the function, and you have peaks that go above that and below that, and you want to know how far that point is above. So like this is our amplitude right here, the distance between this point and the middle line of the function across here. That's 1 unit. Okay. Right. Any questions about your sine parent function? Okay, so we're going to do the cosine one with the sine, and we'll do tangent next week. The reason we're going to do sine and cosine together, if you guys remember when we first graphed them, they look almost exactly the same, and they have a ton of the same characteristics. So because they're so similar, we're going to kind of group them together because graphing them will be super similar as well. Okay. All right, so make another spot for your cosine parent function so you can have the same information for it, okay? And like we said, they're super similar. So at first, this chart's going to look the same. You still want to go one time around the unit circle, and you still just need those guiding values of 0, 1, -1. And those still happen on the unit circle, even if it's the x-coordinate, every 90 degrees. So we still want to count by the pi over 2's for our parent function. But this time your y value is the cosine calculation. So at 0 right here, the cosine at that position is the x-coordinate. The x-coordinate at that position is 1. So this starts at 1 instead of starting at 0. Okay? The cosine at pi over 2 is 0. The cosine at pi is -1. The cosine at 3 pi over 2 is 0. And the cosine at 2 pi is 1 again, okay, because you're back at the beginning. So you see the exact same numbers. It takes the exact same time to get through the cycle. You just see them in a different order. So our graph is going to be scaled the same way because we're looking at the same kinds of information. So still from 1 to -1. And then we'll go through and label our graph the same way. Okay, so I'm going to scale it and then give you guys a little bit to make sure you have the graph and the table and all that stuff. Okay. So it's the same kind of shape, you're just seeing a different little picture of it, starting at the maximum instead of at the middle line. All right, so what is the period for the cosine function? How long did it take us to get through one cycle of the cosine function? Still 2 pi, right? That's why we numbered that much, one time around the unit circle. And again, we're just using the reciprocal relationship for our frequency. And then what's the amplitude of the cosine function? Still 1, right? It looks just like the sine wave, so it has these same characteristics. It just started at a different spot. Okay? So you guys want these in case when you go to do your homework until you learn them well, you're able to have the starting point for each of your graphs of your functions. Everything after that, all the transformations and that kind of stuff, is going to look really similar to what we've done before. You're going to have horizontal stretching, compressing, and shifting, and all those different kinds of things. You're just going to do it with this starting table instead of the other. Okay? So I'm going to put up a cosine graph, and we're going to go through a few things about it. We'll do one cosine example and one sine example. And then if we have any time left today, you'll start your homework. If not, we'll just be working on it all through tomorrow. Okay? All right. Is it okay for me to change does everybody have the parent graphs? Any objections? Because when I click it, it's going to turn this off. Okay. Okay, so the first example we're going to look at is a cosine example, and we'll kind of do it in little like steps. We'll talk about the equation, the transformations, then we'll try to make the charts and find the characteristics, and then lastly we'll try to put it on the graph. Okay, so if you can't see this equation, I know it's a little on the screen. It looks like this. Oops. Not that part. Okay. And so the first step that I wrote down for you guys is to remember to rewrite the equation if there's a b value. And there is, but because that plus 1 isn't inside the parentheses and it's outside the parentheses and there's nothing being added or subtracted to x, there really isn't any need for us to rewrite it. So how it's written is perfectly fine for us to start figuring out the different parts of the graph and things like that. Okay. But then we need to be able to identify the transformations here. It's going to help you two ways. One, you're supposed to be able to do that. That's like one of our requirements. But also, two, it's going to help you know how to measure the period and the different things as they change. Okay. So what kind of transformation does the negative out here cause? So you guys have done a bunch of these. Okay. You also then revisited these with the investigation. Every time you multiply by a negative, what kind of transformation? So it's either a translation, a shift, okay, a reflection, okay. Over which axis here? Good. The reflection would change the y coordinate based on where the negative is in that equation. But when you change the y coordinate of a point, that means you would be reflecting over the x-axis. All right, what does the plus 1 do? Somebody else. Okay. Seth? Good. Okay, so it's a vertical shift up 1. So the whole graph is going to get shifted up 1. Right? Somebody else, what does our 3 do that's in there multiplying the x? So either it shifts stuff, it reflects stuff, or it compresses and stretches stuff. What category does the 3 fall into? So this shifted, right? When you add and subtract, you're shifting stuff. That's not adding and subtracting, right? This reflected, because it was multiplied by a negative. This is not a negative, so it's not a reflection. Okay? So this is either a stretch or a compression, right? Think about how we would use it. It says 3, but remember our investigation when we typed 2 into this thing, it actually took the waves and made them all closer together and made the length of them like a half of what it used to be. So putting a 3 in here is going to make all the waves go closer together and be about a third of what they were before, meaning it's taking them, pushing them together, therefore it's a compression. So we have a horizontal compression. Is everybody okay with how we got the names of the transformations based on the numbers from the equation? Any questions about that? All right, so I'm going to change this and scroll it up, and then we're going to talk about how to get your new tables and all that kind of stuff. And then, like I said, the last thing that we'll do is we'll graph it. All right, so just like we did before, you're going to want to start with your parent function table. You guys already wrote it down, so you should already have this. So this is a cosine function, so I want to make sure I copy the one that's for cosine. So cosine started at the maximum and then cycled through those values. Okay, you guys have it on the other page that we just wrote down. Then, just like we've done before, we want to make a table for our transformed function, which means all those transformations, whatever those numbers in the equation mean, we want to see them transforming the points. So the only horizontal thing that we had when we listed the transformation was based on that 3 that was in there with the x, and it was doing a horizontal compression because it was actually moving all the waves closer together, which is making their wavelength shorter. Okay, multiplying it by 1/3. So remember with that b value, use the reciprocal. And then outside of that, we saw a couple other things. There was a reflection changing the y values by that negative in front, and then there was a shift up 1. All right, so this is how we're going to change the points. So probably the most, I don't know, maybe annoying part about this is you guys are going to have to do arithmetic with these. This one's not so bad because it's just multiplying it, but sometimes you're going to have to multiply and then add something else, So you're going to have to deal with fractions, and those fractions have this pi in them, which bothers some of this. So just take your time and try not to mess up the arithmetic. If you have to write it out, right, so if I'm doing pi over 2, so I want 1/3 times pi over 2, so that gives me pi over 6. And I'm just continuing that idea for each of these. So 1/3 times pi, that would be pi over 3. 1/3 times 3 pi over 2. You can either multiply it and then reduce it, or you can cancel out those parts. So we'd have pi over 2. And then 1/3 times 2 pi gives me 2 pi over 3. Okay. And then the y values are more like what you guys are used to. Okay, so you just have to take these whole integers here, take their opposite and add it with 1, 0, 1, 2, 1, and 0. Is everybody okay with our transformation in the chart? So we're doing the same thing that we've always done. The numbers just look a little more crazy right here. Okay. And then these are the things that we want to be able to know about the waves specifically, and then we'll go ahead and plot them on the graph. So the first thing is the period or wavelength. So you have to ask yourself, did it change from the original one? So this is a cosine graph. Okay. Cosine has a period of 2 pi. That means it takes the wave 2 pi to finish one thing. Did we horizontally stretch or compress the wave? Read your transformations that you wrote down, right? One of them said horizontal compression. So we took the 2 pi distance to make one wave, and we just made it shorter. So the way that you'll do this is you should write down the original period of whatever function it is you're dealing with. So I'm dealing with a cosine function. Cosine has period of 2 pi. And then I have to ask myself, did I squish it closer together or pull it further apart? In other words, is there something multiplying x that caused a horizontal stretch or compression? I did. Okay, I made it smaller by 1/3. And then I'm just going to do exactly here the horizontal stretch or compression that I did right here to the period. So it used to be 2 pi, but you multiplied all the stuff by 1/3. So I'm going to take 2 pi and I'm going to multiply it by 1/3. Two pi over 3. So that's the period. Okay, and I know you guys can see that in the chart. Some of you might be thinking like, oh, that's easy. I'll just do this every time. However, if there's a shift left or right, you're not going to have 0 in your chart anymore, and that might make it a little more difficult. So make sure you understand that you just take the original period and you adjust it according to any horizontal stretching or compressing. Okay. So then the frequency will just be the reciprocal of that. What will be the amplitude for this graph? Sean? It's still 1. So a couple ways that you guys can look. Number one, in our investigation, we learned that the A value is the amplitude, but not negative. So just kind of the absolute value. So because this equation started with a -1 at the front, it's still just a 1 for amplitude. The second thing you can look at is here's the point that's like in the middle. And the highs and lows are only 1 unit away from that. So that shows you the amplitude is also 1. Right. And then the phase shift is literally shifting the graph horizontally. So only if you have an H value will you have a phase shift. You guys don't have that here. So there's no phase shift. Okay. Any question on our points? I have to copy them down so I can move this up to show you guys. So everybody feels like they could make the table of values and they could find period and all that kind of stuff. Okay. So the hardest part about graphing it is probably scaling the graph. So if we look at the graph. All right, I didn't mark anything on it. And it's kind of not in proportion of what you guys are used to. But usually we want to see as high up and down as we do left and right. But for a wave that goes like this and like continuously goes left and right, but starts with an amplitude of 1, unless we have a huge horizontal stretch, we don't really need to see as far vertically as we do to continue the patterns left and right. So a lot of times you see the trig graphs built like this. Okay. The vertical scale, I'm going to just look at my points that I ended up with. So if you guys look in your transform table, you have 0s, 1s, and 2s. So I just want to make sure that I can see everything between 0 and 2. So 0's here at my origin. I'm just going to make this 1 and this 2. And then I know that I have enough room to graph everything. Because remember, the waves go back and forth between the maximum and minimum. They don't like extend upwards or downwards. So if 0 is my minimum and 2 is my maximum, I won't go anywhere above or below those values. Okay? The next thing is how to scale it. So we could just go and write what our parent function is, but remember, we scaled that by like pi over 2, pi, 3 pi over 2, 2 pi. I myself would have a hard time graphing pi over 3 and finding where that is if I've numbered by like halves. If I've numbered by halves, it's hard for me to see where like a third is. So we don't want to do that every time. What we want to do is manipulate the graph, and we want to make the scale as easy as possible. We want to make sure that we put the points on the x-axis of exactly what we have to graph, okay? There's 2 ways that you guys can do this. Way number 1 is by looking at the period, okay? If the period is 2 pi over 3, we normally graph the points from 0 to 2 pi. We know that we want those same amount of points to be graphed in 2 pi over 3. Okay, so normally we go 0, and then we go like pi over 2, pi, 3 pi over 2, and this last one is where the period ends, and it's called 2 pi. We don't want to call that last one where the period ends 2 pi anymore. We would like it to be 2 pi over 3 because we know that that's our new period. Okay, so one way to do it is replace the mark on the graph that used to be the period of 2 pi with the new number that is the period. So always your 4th mark, because that's how many points we graph when we make our parent function table, becomes the period. That's not quite good enough, but that's enough to then give you your scale. So if the 4th mark is 2 pi over 3, you want to divide that by 4 or multiply it by a 4th to see what each mark is supposed to count by. Okay, so when we do that, we would get pi over 6. So if I want my points to be easily graphed on this, every mark should be pi over 6, so that the 4th mark is 2 pi over 3, and I've counted by all the right numbers to find all those points to graph. Okay? Once you figure out what that mark should be, write down that first mark, and then label the rest of your axis. So what this is going to be like is, you know how when we were trying to find like tangent of negative 10 pi over 3 or something like that on the unit circle, and we didn't have that marked on the unit circle? Remember how we'd go around and count in like 60-degree increments, like 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. That's what we can do here. Once you figure out the first mark past 0, that's what you can count by, right? So normally on our graph, this is ones, and we count 1, 2, 3, 4. This is not ones anymore. This is 1 pi over 6, meaning the next mark would be, but 2 over 6 reduces to be 1/3. So I'm going to write that. Okay, so I had 1 pi over 6, 2 pi over 6. Then the next mark is 3 pi over 6, but that reduces to pi over 2. Then the next mark is 4 pi over 6, but that reduces to 2 pi over 3, so that's good. The next mark would be 5 pi over 6. The next mark would be 6 pi over 6, but 6 over 6 reduces to be pi. 7 pi over 6. 8 pi over 6, but 8 over 6 reduces to 4 over 3. And that's how I'm getting my scale, okay? So the key to getting your scale is determining what do I want to count by to make sure it's easy for me to plot all these points, okay? So I gave you guys one way to determine that. One way to determine that is to make your 4th mark always your period, because that's how many points we plot in one period. And then divide it by 4 to figure this out, and then we can scale it. The second way to do it would be to look at your x-coordinates. This chart is actually, sorry, I copied this down there. This chart is actually super helpful because you have 0 right here, and you know the thing that comes after 0 is supposed to be pi over 6. That could immediately tell you how to scale it, okay? But if you didn't have this point in your chart and you just had this, you would basically want to know how far apart each of these are. Like, it's counting by something, and you have to know what it's counting by if you want your points to be really easy to plot on the graph. If you don't have the 0 and you don't like the method I just showed you, the other way to do it would be to take the x values in your chart and figure out how far apart they are. So like, see how I have pi over 6 and pi over 3? I want to know what they're counting by. How do I get from pi over 6 and then get to pi over 3? Then just subtract them. Pi over 3 minus pi over 6. if I change this to a 6, this is like 2 pi. And again, I'd get pi over 6. Okay? So I've kind of showed you 3 different ways to figure out your scale. If 0's in here, it's like a gift. You can see what comes next. That's what you want to count by. Otherwise, you can use the period as the 4th mark. Divide it by 4 to get a single mark. Once you got the first mark, you know what to count by. Third way, take any 2 x values and subtract them to figure out what your x values are counting by and use that as what you're going to count by. Okay? Is this all right with everybody? Otherwise, you're going to end up with one scale on your x-axis, and it's going to be really hard to figure out where to plot those things. Okay? Once you have the positive numbers, you can just mirror those things on the other side. Continue that. Okay? And then just take your points. We're going to plot them. And then we're going to continue the pattern so that we can see more than one period of the wave, but we didn't have to do the table for more than one period. So we have 0, 0, pi over 6, 1, pi over 3, 2. That's not right. Pi over 3, 2, pi over 2, 1, and 2 pi over 3, 0. So there's our points, okay? Meaning this goes like this, because I know what it's supposed to look like. And then I need you to show me more of the graph so I know that you understand the pattern. So all you have to do at that point is continue the pattern to the left or to the right or both. So here it would come back up and then go back down. On this side, it would come back up and then go back down. And so here's what this graph ends up looking like. Okay? When you guys are graphing on like a quiz or a test, I'm going to ask you guys for 2 periods minimum. So your chart will get you through 1, and then just continue the pattern at least 1 time in either direction, like either side of it. Okay? Any questions on what we did here? This is probably the most confusing part of our process right here, is figuring out a scale that we can actually show the graph on. No questions? All right, we're going to do one more, okay, that's a sine graph instead of a cosine graph, but they're super similar, and the idea is exactly the same. So we're going to do all the same steps, but the sine graph has a different parent function. Okay, so I'm going to let you guys start it, and then we'll go. All right, so you guys are going to start it. Same idea as last time. You want transformations. Can you make the 2 tables? Can you find the period, the amplitude, the phase shift, okay, the frequency? Only difference here is this. See how we have that B value, but we also have like an H value? So just a reminder, because some of us forgot to do this a lot first semester when we were working on transformed functions, we need to separate that B value from the X minus H portion. Okay? So when we take the 2 out of X and pi, 2X divided by 2 leaves us with X, and pi divided by 2 would leave us with pi over 2. Okay, and I know that that might seem like, oh, how ugly, but when you think about what we're counting by and times around the unit circle, shifting pi over 2 over makes sense. Like that's something that shows up on our graph often. Okay, so now take this, see if you guys know the transformations. Can you make 2 tables? Can you identify the period, the frequency, the amplitude, and the phase shift, and we'll try to put together a graph with the right scale. Okay, so take a few minutes, work together. All right, so if you guys looked at the equation, these were your transformations. So I kind of just went in order. So like the negative is reflecting over the x-axis. The 2 is going to multiply your y values by 2, so it's a vertical stretch. This 2 that's multiplying x is going to be used like a 1/2. So if we're multiplying x values by 1/2, we're taking horizontal distances and making them smaller or compressing them. The x minus h now says x minus pi over 2. Remember, the minus is part of like the formula we're studying, so h is really a positive pi over 2, and that's why we would shift to the right pi over 2. And then the plus 1 gives us if we shift up 1. If you struggle with the written part, but you're good at making the table, my advice would be to make your table first and then write down transformations from there. So if you knew that this table would include 1/2 x plus pi over 2, and then negative 2y plus 1, I think it's easier to see your transformations once you've written this. Like it makes more sense to me now that, oh, this is a vertical stretch, but this one was a horizontal compression if I see the arithmetic I'm actually doing to the points. And then I see why I'm shifting it right pi over 2 instead of left. So if you can get from there to here, but you struggle with looking at the equation and naming those, maybe write this out if you're good at this, and then go through and name the transformations, because maybe they'll be a little more clear based on what's right here. Okay? And so this is a sine function. So our parent function, the x values look the same as the cosine. The y values actually look the same, but they're just in a different order. So remember, your sine starts at 0, goes up, and then goes back down and ends at 0. Okay? And you'll have your unit circle, so if you struggle with what these are, you'll be able to look them up on the unit circle. And then we're going to take each of these and transform them. The y values are kind of like what we would expect, so I'm going to go ahead and do those ones first. The x values, this is where it gets a little bit tedious and you guys have to be willing to like take your time and go through some arithmetic. So 0 is okay, like 1/2 times 0 is 0, plus pi over 2 will still be pi over 2. When you get to pi over 2, so you need to do 1/2 times pi over 2. So 1/2 times pi over 2 is going to give me pi over 4, and now I need to add that with pi over 2. So I multiplied to get this, and now I need to add that amount. When you add fractions, you need common denominators. So if I want this 2 to be a 4, then this pi has to be 2 pi. And now you can add it together as fourths. It'll be pi plus 2 pi, so it'll be 3 pi over 4. So then when I do pi times 1/2 is pi over 2, and then I'm supposed to add pi over 2 to this. So pi over 2 plus pi over 2 will be 2 pi over 2, which reduces to pi. So I know that's a little weird. You plugged in pi, you did a bunch of stuff to it, ended up back in pi. Remember, this is a compression and a shift. So basically your point at pi got compressed over, but then it got shifted back over, and it ended up back at pi. Okay? 3 pi over 2 times 1/2 would make 3 pi over 4, and then we're going to add pi over 2 to that. Okay, so then again, to add these, we need common denominators. So I want this to be measured in fourths, which means I want the numerator to be 2 pi. So 3 pi over 4 plus 2 pi over 4 will give me 5 pi over 4. And then lastly, I have 2 pi. So 2 pi times 1/2 would just give me pi. And I need to add pi plus pi over 2. It's like that pi has a denominator of 1 right now, so if I want a common denominator of 2, this is 2 pi. So these have 2 in the denominator, and 2 pi plus 1 pi would make 3 pi over 2. Okay? I'm not saying this is like totally fun and like simple and done in 1 second, but you guys all have the skills to do this, but it will take like a little bit of time to just work through the arithmetic. Okay? All right. So let's talk about these things here in the scale of our graph, and then we'll plot the points and be done. So period. So you're graphing a sine function. What's the normal period for the sine function? What's the normal period for the sine function? So normally the sine function, its parent, the parent function has a period of 2 pi. So that will be the period of this sine function also, unless the waves have been compressed or stretched. Okay, so did we have a horizontal stretch or compression? We did by 1/2. So we need to apply that same compression horizontally here to the period. Those 2's will cancel out, and the period of this sine function is no longer 2 pi. Instead, it's pi. Okay? So for the frequency, we would just be looking at the reciprocal of that. What would the amplitude be of this function? Which part of the equation is controlling the amplitude? Like how high and how low the waves go. Okay? The A value should be controlling it, right? So we see that it goes to a maximum of 3, but it was also moved up 1. So the middle's at 1, but then it's going up to 3. So the distance between that middle and that maximum is 2. Remember, that's totally controlled by that a value at the very front of the equation. I know it says -2, but when we measure amplitude, it's like distance. We don't say, oh, I walked a -1 mile to my house. We just say 1 mile or whatever. Same idea with amplitude, so it's 2. Okay. And then phase shifting is literally changing your starting point. So if you look at our chart, instead of starting at 0, this graph starts at pi over 2 for the x because we had that shift right pi over 2. So your phase shift is just the amount that you shifted left or right. Any questions on any of those characteristics? Okay. So what are we going to scale our graph by? So I told you guys last time if you had 0 right here in the chart and you could see what number came after 0, you immediately knew how you wanted to count the graph. We don't have 0 in the chart here. Okay, so we have 2 options. Option number 1 is to figure out how far apart all of these x values are by subtracting them, because then that means that's how far apart we want our marks to be on our x-axis. Okay, 1, 5, pi over 2, 3 pi over 2, I don't know. The other option was to take the period, and remember the period was going to be from 0, 1, 2, 3, 4 marks, because that's where we normally mark 2 pi. And so then to figure out what you want to count by, you can always take that period and you can divide it by 4 to figure out that first marker, okay? Pi divided by 4 would be pi over 4. So I want to count my scale by pi over 4s. If you would rather look right here, take 1 and subtract the 1 before it to see how far apart they are. 3 pi over 4 minus pi over 2. If we make that common denominator, 3 pi minus 2 pi would be 1 pi. My x is here, pi over 4 apart, which means when I count on the x-axis, I want to separate things by a distance of pi over 4. Is that okay with everybody? So you kind of want to adopt one of these strategies that makes sense to you for numbering your axis. Okay? So we're going to go number our axis by pi over 4s. Okay? You guys have the points, and you can tell me the points, right? If I change it, because mine are all going to disappear. Right, so we just figured out the scale. So we'd want to go 1 pi over 4, 2 pi over 4, which reduces, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. And then you could do the same thing the other direction. How high does our graph need to reach based on your values? 3, right? And how low? -1. Okay. And so when we look at your guys' points, we have to plot the point pi over 2, comma 1. So I'll go pi over 2, 1. And then 3 pi over 4, -1. Then pi 1. And then 5 pi over 4, 3, right? And then 3 pi over 2, 1. Okay. So right there, this is our graph. Okay. And we could continue another cycle just by following the pattern. So I could go backwards if I wanted because I have more space on my graph and know from here it would go up, then back down to that middle point, then down to the lowest point, then back to the middle point, and continue following that pattern. Okay? Is all right with everybody? Okay. Did I graph the right point? All right, so tomorrow we're just going to be working on the homework.